Welcome to today's lecture. By the binding authority of paper, rock, and scissors, today I am going to teach you about periodic trends in the sizes of atoms and ions. Before starting, I'd like to tell you a funny story that has nothing to do with anything, but I like to say it because it's funny. Many years ago when I was in high school, a friend of mine moved to my neighborhood from Finland. He struggled with the language and with the culture. Eventually he did come out of his shell, and we've been very, very good friends ever since. One day another friend of mine called and invited our Finnish buddy to come to a high school football game. The Finnish friend said, "Will it be fun?" My other friend replied, Yeah, it's going to be really fun." My Finnish friend then replied by saying, "Then I can't come." Ah, man, I guess Finnish people are allergic to fun. Anyway, with that said, let's get started. As it turns out, atoms get bigger as you go down a column or a group on the periodic table. Why? Well, because atoms, as you go down a column on the periodic table, have more and more orbitals and more electrons. Hence, they get larger and larger. For example, neon's outermost orbital is a 2p, while argon's, which is just below it, is a 3p. Krypton's, which is below argon, is a 4p. Because the principal quantum number n is changing, going from 2 to 3 to 4, it means the orbital sizes are getting bigger. 4p orbitals are larger than 3p's, which are larger than 2p's, and so forth. So as you go down a column, element sizes get bigger. Now, this is kind of not as intuitive, but atoms actually get smaller as you go left to right across a row or a period. As you think about this, you might wonder why. Because as you go across a row from left to right on the periodic table, you're getting more electrons added to each element. For example, oxygen has one more electron than nitrogen, which has one more electron than carbon, and so forth. So you might be tempted to think, well, oxygen should be bigger than nitrogen, and nitrogen should be bigger than carbon because you're getting more electrons. So as it turns out, it's the exact opposite. Oxygen's smaller than nitrogen, which is smaller than carbon, which is smaller than boron. So why is that? Well, the reason is because as I go left to right across a row on the periodic table, elements also have more protons in the nucleus. Furthermore, elements don't get more orbitals going across a row as they do when you go down a column. They do get another electron as I go from one box to the next going left to right, but one electron doesn't actually increase the size of the element. Having more orbitals does. But as I go from left to right across the periodic table, each element has one more proton than the element that preceded it. That proton in the nucleus attract and suck in the electrons more tightly, which draws them further and further in toward the nucleus, and thereby makes the atom smaller. We can see that exhibited in this table, which shows the individual atomic radii of most of the elements on the periodic table. You can see, with some exceptions here and there, there's a general trend as I go left across a row. The elements get smaller and smaller, and once again the reason is because I get more and more protons in the nucleus, which suck those electrons in tighter and tighter and tighter, making the elements smaller. Contrastingly, going down a column on a periodic table, elements get larger, and the reason is because they get higher energy and hence larger orbitals. Orbitals contribute significantly to an element's size. Here's a link to a cute video that shows this clearly. I'll post the link here on our video so that if you want to, you can click on it and go directly to watching that other video. This begs the question, what about ions? For example, do you think a lithium cation would be larger or smaller than a lithium atom? And why? And what about a chloride ion when compared to a neutral chlorine atom? And why? And what about ions going across a row? For example, how would a lithium cation compare to a beryllium 2+ cation and compare to a boron 3+ cation in size? Why? And what about going down a column? For example, how would a fluoride compare to a chloride compare to a bromide in size? And why? Though I'm not going to answer these questions for you here, I will post a link right here to a separate video in which I do. I invite you, however, before looking at that, if you look at it at all, to try to make some predictions first. And if you choose not to watch that video, this table here shows the answers. Does it follow your predictions? That takes us to a set of lecture problems from the problem sets that I give my students in class. You'll remember from an earlier video that I asked and explained which will experience a greater Z effective or effective nuclear charge, the electrons in the n=3 shell in argon or in the n=3 shell in krypton. That leads us to the second question. Which of those electrons will be closer to the nucleus? Explain. Next, how do the sizes of atoms change as we move from left to right across a row in the periodic table and from top to bottom in a group in the periodic table? And arrange the following atoms in order of increasing atomic radius. Now for these questions, I'm not going to do them, but invite you to do them on your own. For the students who take this class from me, you're welcome to ask me in class. I'll be happy to help you out. If you guys are just watching this on YouTube, however, you're welcome to post questions in the comment section, and I will be happy to answer. That takes us to our next subject, that of bonding radii. When two identical atoms bond, as seen in this cute little picture, the distance between their individual nuclei, d, divided by 2, equals their individual atomic radius. Physicists have measured the individual atomic radii of different elements, which are shown in this figure, which I happen to have shown you before. Once again, the numbers shown here represent the radii from each nucleus of each of these individual elements to the outermost extent of their largest orbital. To measure then the distance between two bonding atoms, their bond length, we add up their individual atomic radii. That takes us to some problems. Using the table that I just showed you, estimate the arsenic-iodine bond length. Then see how well your estimate compares to experimental bond length for arsenic triiodide, which happens to be 2.55 angstroms. Next, explain the following variations in atomic or ionic radii. Now I invite you to do this on your own first. If you'd like, I'm going to post a link here to a separate video in which I will show you the answers. That takes us to the end of this lecture, so mischief managed. Please stay tuned to our next lecture in which I'll continue talking about periodic properties of the elements from the periodic table. Will it be fun? Then I can't come. Until next time, have an enjoyable rest of your day.